Hello, 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 hello. So far, we've been writing programs that primarily just work with putting values in a register, manipulating the value, maybe putting it in memory, pulling it back out, and editing it, or outputting it, or editing it again. But what happens when you have a function that calls another function, that calls another function? How do we keep track of all of those values? Because after a couple of times, you have to remember, oh, this is X values away, and this variable was, oh, the second variable in this last function, but the third variable in the function before that, but the first value was here. It gets very confusing very quickly. And so one way that we deal with this is we use what we call stack frames. And what a stack frame is it's an area of the stack that a function owns, quote, owns. And that part of the stack that the function owns is there to save its own variables and keeps everything pretty nice and tidy on the stack. This is very easy to see in a function that keeps calling itself, because what we'll see is we'll see a repetition of stack frames. And so I chose the Factorial's function, which is fairly standard for teaching recursion. And for this, we're actually going to be looking at the values in the memory. And so let's get started with this. We have, as we start, just the start and the max number. So let's plan this out a little bit. The first thing that we need to do is we'll need to load the number into a register so that we can do something with it. Then we'll need to start our first stack frame. And what we'll actually do with this is we're going to take what the stack pointer is pointed at and just save it. Using the magic of post-production, what we can see is that when this program is first loaded, the stack pointer is pointing to the number 1 in memory. What this number 1 is showing us is that there was one argument passed to the program. When Linux opens a program, the first argument that you have on the stack frame is the number of arguments passed. And the first argument is always the name of the executable. And so that's what we would see if we looked at the memory. So the first thing we're going to do is we'll put the max number in register 0. And then here, we're going to put into R12 the value in the stack pointer. As you know, the 13th, 14th, and 15th registers are used for different purposes. One of them is the program counter, one of them is stack pointer. And so what we're going to do is we're actually going to use R12 as our frame base pointer. So as of right now, our frame base pointer and our stack pointer are pointed at the same part of memory. What we're going to do, though, is we're going to call our factorial function. As opposed to moving the value that we want to use into one of the first registers, which is what we have been doing when we call procedures, what instead we're going to do is we're going to push the value, the first argument, to the factorial onto the stack. And since that's in register 0, we'll just do push register 0. And then we'll go to our factorial, and we'll just call it factorial. So what we need to do is we actually need to define our factorial function down here. So the first thing that we need to do is we need to close out the frame of whatever just called us, or where we're going to return to. To do this, we need to push two values onto the stack. The first thing that we need to do is we need to push the address that we're going to eventually return back to when we go back to the start function in code. And so right now that's stored in our link register, so we can just push that. And then the other thing that we need to push is we need to push the old frame base pointer to the stack. And we need to do this so that when we're done with this function, what we can do is we can return back to the other function and have the same reference in our variables. And again, our frame base pointer is going to be an R12. And so what you can see right now is that we have our first parameter, 9, which is getting passed to the factorial. And then after that, we have where our code is going to jump to after we're done running this factorial loop. And then we have our old base pointer, our frame base pointer, which points to the frame base of our main or our start function. After that, what we need to do is we need to start our new frame base for the factorial function. And again, all we're going to do to accomplish this is we're going to store in R12 whatever the stack pointer is pointing to right now. The next thing that we need to do is we need to access the number that we had pushed for this calling of the factorial. And if you look at this, our parameter, our 9, is 2 blocks above where our stack pointer, our frame base pointer are right now. If we want to call that, we can try and figure out what memory address it's going to be at. But we know, since we only have 2 more values above it, that it's always going to be 8 bytes above where we're at right now. So let's put that in register 0. Our frame base pointer, and then 8 bytes above that. If we were writing this out in a pseudocode, it would be, if the number we're passing in is 1, then we just return 1 and then go back to what we're doing. If it's not 1, however, what we need to compute is essentially x times factorial of x minus 1. So let's put both of them here so that we can do this in a second. So let's do 1 first. What we can do is we can use the compare opcode, and we're going to compare whatever we loaded into register 0 to 1. And if we do have 1, then we just need to go to the exiting of this subroutine, however we do it. And we'll just call it fexit for function exit. However, if it's not, we essentially have to call the factorial function again. So what we're going to do is we're going to do the same thing that we did before. We're going to set up our call and make the call again. So if you remember what we did before, the first thing that we pushed was the number that we want to pass to the factorial. However, this time you can see that we have two x's in this. We have x times the factorial of x minus 1. So we need to save that first x as well. Before we set up the call to the factorial, we need to save that x. And so we're going to push the value of r0. And what this does is it saves x for the return statement, for the x times factorial x minus 1. And right now, this is, if we wanted to access it, it's at the base pointer, the frame base pointer, and 4 bytes below that. Remember that the stack grows down and the heap grows up. So as we add things to the stack, our memory goes down, 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 down. The addresses go down, down, down. Now we can pass the number that we want to pass to the factorial function. And as you can see, it's x minus 1. So let's subtract the 1 now. So we're going to subtract from r0, 1. And then we're going to push this. And this is where you can see we're going to do the exact same thing that we did before we called the factorial function. And this, if we were to calculate it, it's in the frame base pointer minus 8. The next thing that we want to do is call the factorial function. Factorial. And so you can see right now what's going to happen is that it's going to go back up to the beginning of the factorial function. It's going to save the link register, and it's going to save the old frame base pointer. We're going to get a new frame base pointer because it's going to move to where the stack pointer is at. We're going to load the old value, which is in the same place because we called it in the same way, right? Because we pushed the value we wanted to process after the local value of factorial 9. And then we're going to do the same thing. We're going to say, is it 1? If it is 1, we'll jump to the exit part that we haven't written yet. If it isn't 1, we're going to do the same thing. We're going to save the current value. We're going to decrement it by 1. And then we're going to push that so that the factorial subroutine will pull that param. And it'll just go on and on and on and on until it gets down to 1. So after we get this, after we get the value, what we need to do, just like it says, else x times factorial times x. So when we get the value of factorial x minus 1, we actually need to do the multiplication. And so we also need to, quote, remember where that value was. So we haven't done the closing part of this function yet. But we do know that because we use our stack frames, that this value is going to be at the base pointer, the frame base pointer, minus 4. So we can recall that by using load register. And we'll put this into register 1. Our frame base pointer, which is at R12, and then minus 4. And you can see right now kind of where the benefit of this is if you go ahead and plan what your strategy is, then you don't have to worry about this every time that it goes through. You always know that this parameter is going to be 4 bytes off from the frame base pointer. We can then multiply it, and we'll put it in R0. And what we have is in R0, we have the result of the factorial call. and then R1 is the recalled X variable. And then what we'll do is we'll go to the function cleanup, which we'll just call fexit. Because the next line is fexit, or whatever this cleanup material is, technically we don't need the branch call. And actually, I believe probably in many linkers, this may even get optimized out because it's essentially a no operations because it's just going to the next line. I like including these things just for readability. Even if it doesn't optimize it out, it's not going to have any significant amount of time, resources, anything like that. But I think it makes it very much easier to read. How do we unravel this web that we spun? The first thing that we need to do is we need to reset our frame base pointer. So what we're going to do is we're going to move into our stack pointer the value that's in our frame base pointer. In post-production magic, we'll see how well I can show this. What this will do is it'll take where the frame pointer is and it's going to move it up in memory. And what it does is it essentially frees those bytes of the stack. And so now we're back to where we were the last time that we called this function. And this is a couple of things. First of all, we don't have to keep track of what variables on the stack we're using and which variables we're not using. We know that if we've moved our frame base pointer back to the call before it, then we don't have to keep track of any of the variables that would be lower on address space here because we're back here, which also makes it easier to reuse with a different factorial call or a different function altogether. The next thing that we need to do is restore our old frame base pointer now for the call before it. We've already notated where the stack pointer would be, but now we have to actually restore the value of our frame base pointer. And to do that, we're just going to pop off the next value on the stack and put it in R12. And then the next thing that we need to do is we need to get back to where we were at when we were executing the code. And so we're going to get our link register. And then we're going to branch and exchange to that point. And so that's pretty much it. It doesn't seem that difficult, but by using a method like this, it can save you a lot of time, a lot of headache, a lot of problems with memory management by not having these long-term variables. There's times where you'll need to use memory to store variables for a longer time or larger than what can be fit into the stack. You can use addresses that point to different parts of memory, maybe a string in memory, but this is one of the very basic memory management tools when you're calling other functions with stack frames. With all that being said though, let's finish out this program. We're going to set up our integer to ASCII. And remember, by doing that, we move into register 0, the number that we want to display. For right now, the factorial returns that number back to R0. And so this is actually no op, but this is another time where I do it just so for clarity. The next thing that we want to do is we want to set up the address that we want to store the ASCII to. And at the bottom, we've already have some space there. So what we're going to do is load register into R1, the out string. After that, we'll jump to the integer to ASCII. And remember that we'll save that to memory, so we don't have to worry about that. And the next thing we need to do is write the number. So we're going to move into register 7, number 4. And remember, for the system call, 4 is write. We're going to write it to standard out, which is 1, and that goes into register 1. Oh, I'm sorry, register 0. And then the next parameter is the address of the text that we want to write out. So we'll go, and again, this is already in register 1 from before, so this is also a no op, but again, something I like doing just so that I can see that it is there. And then the last thing that we need to write to our write system call is the length. And we have reserved 11 bytes because that's the longest number that we could have here. And then we need to call the supervisor. And that'll print out the number. The last thing we need to do is just clean up everything and exit gracefully. If this were part of a bigger function, or if this were another subroutine, what we'd have to do, of course, is also clean up the stack frame here. And that would be the same thing that we did at the ending of the factorial, resetting the stack pointer, restoring the old base point, and restoring the address to go back to jump to when we execute it. Because this is the end of the program, we just have to exit. So our supervisor call for this is 1. And then we have no error. And so into register 0, we'll put 0. If I can type. And then just call the supervisor. Hopefully, this works fine. We have 362.880, and we should be looking at 362.880.